Okay, in this example, you're given a man on a motorcycle is attempting to make a turn on a level road while moving with a speed of 80 km per hour. Okay, so we know that the man is going to make a turn, so he will describe his part of a circular motion. On a level road, this will suggest that it will be a horizontal circular motion. Okay, you're given the radius of the curvature is 20. The combined mass of the man and the motorcycle, the combined CG as shown in the diagram, is here, so it's 350 kg. The distance from the CG to the point of contact of the motorcycle with the ground along the central line of the motorcycle, so this is a central line, so you're told the distance from the CG to the point of contact is 0.65 meters. Okay, let's take a look at the first question. Part A. Find the magnitude of the centripetal force required for the turn to take place. Okay, in part A here, slightly different. We need not draw free body diagram in order to find the centripetal force. Because here, if you refer to the question, we are given the mass m, we're given the radius r, we're given the speed v. So we can actually make use of mv squared over r to find the centripetal force. Okay, the v is given in kilometer per hour. You need to convert that to meter per second. So with that, we get the centripetal force to be 8640 Newton. Let's take a look at part B. What is providing the centripetal force in this situation? So we take a look at the free body diagram for the motorcycle. I will have the mg, which is the non-contact force. The motorcycle is in contact with the ground, so there will be a normal contact force. Okay, normal contact force, as the name implies, it must be perpendicular to the surface, pointing away from the surface. Okay, if I only have normal reaction force and the weight mg, you can see that both these forces are in the vertical direction, so there's no way that the motorcycle can turn in a horizontal circle. So there must be another force. Okay, this force that I label here, this is the friction. The friction must be directed towards the center of the circle to provide the resultant force, which is the centripetal force that is necessary for the motorcycle to turn, okay, to change the velocity. So the centripetal force is provided by the frictional force between the tires and the road. Okay, let's take a look at part C. Why must the motorcycle bank into the turn instead of remaining perfectly upright? Okay, over here you can see that I have a diagram whereby the motorcycle is perfectly upright. Why can't the motorcycle be perfectly upright when it's turning? Okay, compared to the motorcycle tilt at an angle. Okay, this is usually what we see when the motorcycle is turning. The motorcycle together with the man will be tilting at an angle. So why must it tilt at an angle? Why not upright? To do that, let's again consider forces acting on the motorcycle. So we have the weight of the motorcycle and the man, the normal reaction force, and the friction. If I take moment about the CG of the motorcycle, okay, to check whether it's in rotational equilibrium, I will see that okay, both mg and n produce no moments because the line of action of the force pass through the CG. But the frictional force, okay, will provide a moment, okay, because of the perpendicular distance between the CG and the line of action of force. So there will be a moment that actually cause the cyclist to turn in this direction, which is the clockwise direction. Okay, what happens when the motorcycle is tilted at an angle? That means it bank into the turn. As can be seen in the diagram, okay, if I were to take moment about the CG, mg will not give you any moment. The friction will give me again clockwise moment. But then there's another force here, which is the normal reaction force. The line of action of the normal reaction force does not pass through the CG. In fact, there is a perpendicular distance, okay, from the CG to the line of action. It is here. So this normal reaction force will provide a moment, in this case anti-clockwise moment, that counterbalance the clockwise moments produced by the friction, and therefore when the motorcycle turns, it can be in rotational equilibrium if it is tilted at an angle. So for that reason, it cannot stay in the upright position because there is an unbalanced moment that will cause the motorcycle to turn. Okay, so this is the answer that is printed for you in your lecture notes. The motorcycle must bank, that means must tilt into the turn, so that the clockwise moment of the frictional force F about the CG is balanced by the anti-clockwise moment of the normal reaction force N, also about the CG of the motorcycle. Okay, let's take a look at D. You are asked to find the required banking angle theta. Okay, now we know that the motorcycle got to be tilted at angle theta, right? So we are asked to find what is this angle theta that is between the vertical line of the earth and the vertical line that is the line of symmetry that passed through the motorcycle. So what is this angle theta? In order for the motorcycle to remain in rotational equilibrium and not topple over. So again, for circular motion, we require a centripetal force. In this case, is provided by the frictional force. So we have F equals to mv squared over r. And for vertical equilibrium, mg must be equals to n because the resultant force in the horizontal direction is 0. Then for rotational equilibrium, net moment is 0. So the frictional force F multiplied by the distance, okay, the perpendicular distance. We know that if you look at this triangle, you know the hypotenuse here, this is given as 0.65 in the question. Okay, this angle is theta, so alternate angle, the angle between the mg and the vertical axis of the motorcycle will be theta also. So I make use of trigo. 0.65 cosine theta will give me the vertical distance between the will give me the perpendicular distance between the CG and the friction. Okay, so I have 0.65 cosine theta times F. So that will give me the clockwise moment. Then the anti-clockwise moment will be n times again the perpendicular distance. Same thing, you make use of this triangle. Okay, hypotenuse is 0.65. I want the opposite, so it's sine. So I end up with 0.65 sine theta. So the equation that I have is F cosine theta equals to n sine theta. Okay, we want to solve for theta. We don't have frictional force, but we have centripetal force. So I'm going to sub equation 1 into here. I will have mv squared over r, or you can just use the magnitude that you calculated in part A here. Cosine theta equals to n, the normal reaction force I don't have, but for vertical equilibrium we have normal reaction force to be equals to mg. Okay, and this whole thing is sine theta. So solving, we have tangent theta equals to v squared over rg. Notice that this equation tangent theta equals to v squared over rg keep appearing, but I would not advise you to memorize this equation because it can be obtained easily from the free body diagram as well as the rotational equilibrium equation. Okay, so from here to get theta, I make tangent theta the subject. Okay, velocity is given, convert that to meter per second. Radius is given, g is known, 9.81. So from here I work out the angle to be 68.3 degrees.